Theorem 1.3. Let X be a locally compact Hausdorff space in which every open set is sigma compact. Let lambda be any positive Borel measure on X such that lambda k is finite for every compact set K. Then lambda is regular. Then lambda is regular. Proof. Define as usual lambda from C X to C as lambda of f equal to integral x f d lambda for every f belongs to CCX. Okay. As we know that lambda k is finite for every compact set. Since lambda k is finite for every compact set K, lambda is well defined. Clearly, lambda is a positive linear functional on CCX. Okay. Again, we will appeal to Rees partition theorem. Thus, in view of Rees representation theorem, what we get? And the fact that X is sigma compact. Because why? Because X is open. There is a regular measure mu such that integral x f d lambda is equal to x f d mu for every f belongs to CCX. In this case, measure will be regular. Okay. What will show? We show that lambda is equal to mu. Okay. Okay. We show that lambda is equal to mu. Let VVN, to show this, let VVN open set in X such that Okay, let V open set in X. Then we can write V as union of these compact sets. For compact sets Ki. Okay, as you know that every open set is sigma correct. So why Urson's lemma? Why Urson's lemma? Urson's lemma. Urson's lemma we can choose Fi such that Fix equal to 1 for all x belongs to Ki, and support of Fi is contained in V. Okay, this is my Urson's lemma. Let Gn equal to maximum of F1, F2, these are so on to Fn. Then clearly each Gn belongs to CCX. Then Gn belongs to CCX and it is increasing, and Gnx increases to x function of over Bx at every point x belongs to x. Okay, now lambda of V you can write as limit n tending to infinity x integral Gn d lambda. Okay, so while monotone convergence theorem integral x you can write limit n tending to infinity. First write like this. Now why monotone convergence theorem? Write like this. Monotone convergence theorem and the integral we are using, put this as 1. No, not this one. This one. Put this equation 1. Theorem and equation 1. We get integral x limit this. Now this is we know that integral this one Gn is equal to limit n tending to infinity Gn d mu, and this is the theoretic equal to mu of V. Okay, so we this get for open set lambda V equal to mu of V. Let EVA Borel set in X and epsilon equal 0. What we are given? We are given that X is sigma compact. Okay. Then as X is sigma compact, there exists a closed set. There exists a closed set F and an open set V such that F is contained in E is contained in F is contained in E is contained in V, and with V of V minus F less than epsilon. This you know. Okay. This implies mu of V is less than equal to V of F plus epsilon, and this F is set of E, this is less than equal to mu of E plus epsilon. Okay. Put this equation number 3, this equation number 2. Okay. Again, since V minus F, again V minus F, yes, is open. It's open. We have from from 2, equation 2. What do you have? We have from equation 2. Yes. See, where is equation 2? This one. Lambda of V minus F, equation 2. Okay, this one. Correct. We get lambda of V minus F is equal to mu of V minus F, and this is less than epsilon. What this implies? This implies lambda V, yes, lambda V is less than or equal to lambda of E plus epsilon. Okay. Correct. Okay. Now put this equation as 4. Thus from third 3 equation, thus from this is equation 3. Mu of V is less than mu of E plus epsilon. Okay. From 3 and 4, we get lambda of E is less than equal to lambda of V equal to mu of V, and this is less than equal to mu of E plus epsilon, and mu of E is less than equal to mu of V, and this is equal to lambda of V, and this is less than lambda E plus epsilon. What epsilon greater than 0 was arbitrary. Okay. We conclude that what is that? Lambda of E is less than equal to mu of E, and mu of E is less than or equal to lambda of E. And this implies thus what you get? Lambda of E equal to mu of E. This implies lambda is equal to mu. What do you get? Mu is regular and mu is equal to lambda, so lambda is also regular. And since mu is regular, so is lambda. Okay, this finishes our proof of the theorem.